Okay, on this foggy, rainy morning, continuing with quantum thermodynamics, and we need to put in place all of the thermodynamics infrastructure, things like statistics over ensembles, things like thermodynamic equilibrium. And so what we start with is taking the classical result from the 19th century, Boltzmann equilibrium, and porting it to quantum mechanics. So the first item on the list today is thermal equilibrium. Well, as Mr. Boltzmann tells us, if we have a set of energies in the system, and in our case those would be the eigenfunctions and eigenvalues of some Hamiltonian, and you know how to do that by now. You've done that many times in your various courses in continuous as well as matrix representations. Boltzmann tells us that the probability of finding a system in a particular energy level is the exponential of minus z energy over kT divided by the partition function, and that is also something that has been mentioned to you already. It is a sum over n of exactly such exponentials, and essentially just let's make it a sum over k so that we do not collide any indices there. K, B, T. And although this partition function in the denominator simply serves here as the normalization, it has fundamental significance in thermodynamics, as you know, in that all of the functions of state, temperature, pressure, Gibbs free energy, entropy, and so on, are derivatives of this function. Okay, this is all classical. How do we make this quantum mechanical? Well, remember what our density matrix physically meant. On its diagonal, it had probabilities, so P1, P2, and so on Pn, however many energy levels we have in the system. And the off-diagonal elements were correlation coefficients between different molecules across the ensemble. Well, in thermodynamic equilibrium, we expect such correlations to not exist. Enough molecules have bumped into the various walls and randomized themselves sufficiently that off-diagonal elements of the density operator would be zero. And so we have only probabilities to put on the diagonal, and we do know the expression for those probabilities. So how do we construct such a matrix? Well, let us ask ourselves a technical question. Okay, we know this diagonal element. How do we build algebraically a matrix that has that diagonal element? Well, we have to remember once again how to multiply the vectors the wrong way around. So if I multiply a column with an element k, right, by a row with likewise an element k there, so case element here, case element there, then the result, let's think about it. So 0 times 0, 0, 0 times 0, 0, and then finally there is this element here times this element there. It will create an element in position kk. So k, k, and if we have a unit here, so 1 and a 1 here and zeros everywhere else, then it's going to put us this 1 on the kk place along the diagonal. And of course what this is in practice is our wave function psi n, the basis function, which in some vector representation would have all zeros except for a single one somewhere corresponding to that energy level. So that's the ket, and that is the corresponding bra. So that is psi n, psi n. And that would give us the matrix with a unit in position n. Well, let us put all of that together. So our thermodynamic equilibrium density matrix is therefore going to be literally that sum. So sum over all energy levels. Then we want this number on the diagonal, so we want it multiplied by that. So we would have e to the minus en over kbt times psi n, and then divided by this partition function. So a sum over k e minus ek over the Boltzmann constant times the temperature. Okay, so far so good. Let us ask ourselves now what this is. In the numerator, we have a matrix with the exponentials of energies on the diagonal. Well, but the matrix with the energies on the diagonal is the Hamiltonian in the basis. So this is in fact the matrix exponential of the Hamiltonian. Okay, that's a simplification. So we have E minus the Hamiltonian matrix over kBT. And we have discussed the meaning of a matrix exponential in the previous lecture. It is defined as the Taylor series. Still divided by that sum over all energy levels of these exponentials. But these exponentials occur on the diagonal of this object, so that is simply a sum over all diagonal elements of this, and that's a trace. So that is actually 1 over trace of E minus H over K dt times E minus H over K Boltzmann T. And so we have suddenly, without too much difficulty, derived both the expression for the equilibrium density matrix, just the exponential of the Hamiltonian divided by some normalization, and the expression for the quantum statistical partition function. And these are both central to a lot of computational chemistry and to the entirety of magnetic resonance, of course, because they pertain to finite temperature. And in a lot of cases, our molecules would not be in their absolute, zero ground state. There would be some distribution over some excitations. And if we would like to calculate some average observables at a finite temperature, this is what we would have to do. To obtain that equilibrium density matrix, which then would give us the observables when we multiply it by some operator and take the trace. Okay, now remember what I told you about these energies at the very, very beginning. In magnetic resonance, they're tiny. At room temperature, kT is a few kilocalories per mole, and that is significantly smaller. Let us take advantage of that and derive the high temperature approximation to that. So let me remind you of a parameter in thermodynamics that is commonly used for such expansions to just facilitate the mathematics. So 1 over kBt is often called a beta, and that in our case is a small number. So our row equilibrium will be E minus beta H. You can see how the notation simplifies, right? Over trace E minus beta H. And let us do a Taylor series of this to the first term. So approximately equal to a unit operator minus beta H, and then plus something of the order of the norm of H squared, so we neglect those parts. And then in the denominator, we would have a trace of, once again, a unit matrix minus beta H plus something else that we ignore. Let's look here. this unit lives, that beta h lives. In the denominator, the trace of the unit lives, but remember all of the operators that entered spin Hamiltonian were traceless. They were all Pauli matrices and spin operators, and for Sz, for example, 1/2 minus 1/2, right? The trace is 0. So the trace of that is 0, so we just are left with the trace of 1. So we have here, once we ignore that thing, minus beta h, and then trace of a unit matrix, which is literally just the number of energy levels in the system. So the matrix itself has the dimension equal to the number of energy levels. The unit matrix has just ones on the diagonal, and its traces therefore the number of energy levels. So that is a normalization. And you can see that the deviation from the unit matrix here, the one in which every energy level is equally probable, is proportional to the Hamiltonian. As you can imagine, right, if the energy is slightly higher, then because of this minus, the corresponding probability would be proportionally lower to first order. That makes physical sense. Okay, that is thermodynamic equilibrium and the high temperature approximation. Generally valid for nuclear magnetic resonance at almost any temperature, and for electron spin resonance at room temperature. If you do freeze electrons down in liquid helium, then that does break, because there the energies actually are somewhat bigger than the thermal energy at very low temperature. But for NMR spectroscopy, for all intents and purposes, we have this. Another approximation, so this is high temperature approximation, so high T approx. The other approximation we need to cover pertains to this unit matrix here. Let us think about what it means and what it does. Firstly, for observables. If we take some observable quantity, remember it was trace of the corresponding operator times the density matrix. And all of the observables in magnetic resonance are traceless. So what we are going to have there is it's going to be proportional, so I don't worry about the denominator, to trace of this operator O, and then the unit matrix minus beta H. So for thermal equilibrium, for example. And then this splits into trace of O times the unit matrix minus beta trace of O times the Hamiltonian. But let's think about what that is. The unit matrix is a unit matrix. It does nothing to the operator O. Operator is traceless, and so that is 0. So the presence of the unit contribution to the density matrix does not influence the observables. So no effect on observables. The second thing that we would note is that d by dt of the unit matrix from the Liouville von Neumann's equation, remember minus I, the commutator of H with the unit matrix, and that is 0, because everything commutes with the unit matrix. And so it turns out not only does the unit matrix not contribute to any observables, it also doesn't evolve. And on the summary of these two, we can just ignore it. So traceless approximation is that we simply drop the unit matrix contribution from the density matrix. This is allowed only at high temperature and only in situations where we do not have sophisticated relaxation processes like dynamic nuclear polarization. But for a lot of NMR and MRI, this is quite sensible. So in a lot of cases, you will see that we are at high temperature and we are traceless. Okay, that was the thermodynamic part. Now, item 2 on our list today is spin state classification. About what they are, what they mean, in light of all of the statistical arguments that we have just made about it. Now, I will remind you from the previous lectures that we have arrived, after some philosophy, at the conclusion that if we take two systems A and B and we put them together, then in the composite system, every state of subsystem A can coexist with every state of subsystem B, so it's a full list of all combinations. And such a list is called a Kronecker product. So we have psi A, Kronecker, psi B. And closer home in magnetic resonance, what that simply means is that if we have a spin half here, and we have alpha and beta states for that, and we have spin half there, we have alpha and beta states for that, then all the possible combinations of them end up in the composite system. So alpha, 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 beta, beta, alpha, and beta, beta. And likewise for the expansion coefficients. If we have a basis set with some coefficient here and some coefficient here in the linear combination, likewise there, so we can rewrite it, for example, A alpha, B, or A beta, such that A alpha absolute square plus A beta absolute square is equal to 1. So normalized linear combination, A alpha times alpha, A beta times beta. So Kronecker, some B alpha and B beta for the second system. Then we would have the corresponding products here, C alpha alpha, C alpha beta, C beta alpha, and C beta beta, where these C's, so C alpha alpha is A alpha times B alpha. And then, of course, the normalization of these two, so norm squared of B alpha plus norm squared of B beta equals 1. The combination of that and that will then necessarily lead to the normalization of this product. So the sum of absolute squares of those will also be equal to 1, and we will prove it in the workshop as one of the problems there. Okay, now let us think about what this means for the density matrix, and then think about the physical and statistical meaning of such a construction. For the density matrix, it's quite simple. I will remind you of the properties that we have proven in the workshops. So A cron B, C cron D. Kronecker product commutes with the standard matrix multiplication. So this is AC cron BD. They're just multiplied term by term when the dimensions are compatible. And the trace of a cron B is just a product of traces. Trace A, trace B. Also easy to prove, and we will do that in the workshop. Okay, for the density matrix, therefore, if we take rho A, B, well, let's just go from the definition. This is psi AB, psi AB. So the definition of the density matrix. Then substituting in the expression for psi AB from there. So that is psi A cron psi B times, likewise, psi A cron psi B. Using this property here, we get psi A times psi A cron psi B times psi b. And of course, that's the density matrix of subsystem A. That is the density matrix of subsystem B. This is rho A, Kronecker, rho B. And that makes perfect physical sense. Remember, the elements of the density matrix are probabilities and correlation coefficients. When we are looking at combined behavior of multiple systems, probabilities multiply. And so the table of probabilities of A will be combined multiplicatively in every possible way with the table of probabilities in the system B. And so the probabilities of collective states will just be every possible product of individual probabilities inside subsystems. So that makes perfect sense. And then the Hamiltonian of a composite system is just obtained, I'd say, at our level here from physical intuition. We want the operators of A to only act on A and not on B, and the other way around for the operators of B. And so our Hamiltonian of the composite system will be HA Kronecker unit matrix acting on B plus unit matrix acting on A, Kronecker the Hamiltonian of the subsystem B. And that has the requisite properties in that the first term here acts on subsystem A, does nothing to subsystem B. Second term the other way around, and of course the energies have to be additive, and so we have to add them up, and that is our Hamiltonian for the composite system. And we've built similar operators in the previous lecture. Remember how we constructed the J-coupling Hamiltonian when we were dealing with that, I think earlier this week. We had Hj of A and B, and then it is an inner product of the two magnetization vectors that would correspond to the crons there, so 2 pi j, and then Sx1 cron Sx2 plus Sy1 cron Sy2 plus Sz1 cron Sz2. And we dealt with them explicitly a few lectures ago. So if we want the X observable on spin 1, X observable on spin 2, and we want them multiplied, that relation kicks in, and we have that construction. This is all very computer friendly, because one of the things that computers can easily do is this kind of direct product matrix multiplication and construction of such combinatorial arrays. Okay, so this is how we build the states of composite systems, the Hamiltonians of composite systems, and interactions between the components of those composite systems. Now let us take a look at their physical meaning. Common classification, and that's historical, defines the following types of states. So, classification. So A, longitudinal magnetization. And these are states that do directly correspond to observable magnetic moment. And those would be things like SZ1 or SZ2 or whatever. Therefore, nuclei, electrons, and so on, they directly correspond to longitudinal magnetization, nothing special. The interesting states are the direct products of individual spin operators, which occur, for example, in the J-coupling. They're called longitudinal correlations, and this is something we need to discuss. So, longitudinal correlation. And you will see this a lot, and it is not often properly explained. Let us take a look at a state that looks like that. SZ Kronecker, SZ. This on spin 1 and that on spin 2. And this occurs, for example, in the J-coupling. Let's think about what the physical meaning of this is. If we calculate its trace with any of the standard observables, Sx, Sy, Sz, we will realize that the trace is 0. So this does not actually correspond to any observable magnetization. But let us think about what it corresponds to. So Sz, Kronecker Sz, is 1/2 minus 1/2, 0, 0, from 1/2, 0, 0, minus 1/2. And if we write that out, we're going to have a quarter, minus a quarter, minus a quarter, and then a quarter again, and zeros everywhere else. And remember this traceless approximation business, right? When we take these direct products, the trace is not there, so we need to add just enough unit matrix to this to make the trace equal to 1, to balance out the probabilities. So I will add a unit matrix divided by 4. As per the previous discussion, this does not evolve and does not influence the observables, so this to us is a cosmetic transformation that would simply balance out the probabilities. So we are going to have 1/2, 0, 0, 1/2. And what did it physically mean? Well, this state was alpha alpha, that was alpha beta, that is beta alpha, and that is beta beta. So you can see that the probabilities of the two spins being collinear in whatever direction, either up or down, are non-zero. The probabilities of them pointing in the opposite direction are 0. And so this is an interesting state which does not actually specify which direction the spin has to point in. It only specifies that whatever direction they're pointing in, they have to be pointing in the same direction. So their direction is unspecified but correlated. And thus, this is called longitudinal correlation. So we are looking at a statistical property across the spin ensemble that didn't necessarily correspond to any overall magnetization of the sample. So the spins can point anywhere so long as they point in the same direction. And of course, that is then physically the explanation of why this Hamiltonian does move our energy levels. For the magnetic moments to interact one way or another, you know that collinear magnetic moments have high energy, antilinear magnetic moments have low energy, and this is why this J-coupling Hamiltonian contains correlated terms. It doesn't care which direction they're pointing in, it only cares if they're pointing in the same direction or not. Right? So that is the explanation for those terms in the Hamiltonian. Likewise, we have for transverse exactly the same physical meaning and exactly the same explanation. So see transverse magnetization. So things like Sx, but also S plus minus. They are not Hermitian, but they are useful in magnetic resonance to cut certain corners in the data processing. So this is Sx plus or minus Isy. I would remind you, so it's a complex linear combination of transverse magnetization terms, and they are occasionally used, even though they are not strictly speaking Hermitian. Likewise, transverse correlations. So see D. So things like Sx, Sy. Sometimes we write the Kronecker products in between them, but most chemistry textbooks do not, so you would see terms like this, Sx, Sy, without the Kron in between, because, well, plainly the Kronecker products require a lot of explanations and they scare some chemists, and so a lot of textbooks just skip them because if you are not going into literally these matrices, there's no point terrifying the poor biologists with matrix outer products. Okay, so transverse correlations, and then of course there are mixed states. Right, so you can have, for example, the transverse state of spin 1 correlated with the longitudinal state of spin 2. So wherever they point, they're at liberty to point, so long as they're, for example, perpendicular to each other. And so that would correspond to mixed correlations. So things like Sx, Kronecker, Sz. That's spin 1 and that's spin 2, etc. There's plenty of them. And we will encounter all of this when we do protein NMR spectroscopy, because all of the two-dimensional pulse sequences in magnetic resonance, they make use of these states in order to push the magnetization around. So if we have two interacting spins, we start with the magnetization of one, we move it into a correlated state, then we apply a few pulses and we can then withdraw from the original spin, and that moves the magnetization from one spin to another. Okay, there are a couple of historical names which I need to mention. We've already come across these correlated states. A particular type of correlated state is called the coherence. And the definition is somewhat obscure if we have such a state that if we commute it with the total Sz in the system, so commuting with the density matrix, if that returns us a multiple of the density matrix, that's called the K quantum coherence. An equivalent definition of that, so in here Sz is the total Z, so Sz is the sum over K, Sz on every spin. An equivalent definition for this is when we are evolving such a state under a standard Zeeman Hamiltonian. So if, say, we have a two-spin system, it will be E minus I omega 1 S1 Z plus omega 2 S 2Z times T. So remember the exponential propagator applied to the density matrix, and then E plus exactly the same propagator. Then that evolves at the sum of the two frequencies, omega 1 plus omega 2 T rho. Again, a somewhat obscure definition and a somewhat obscure state, but let me give you the physical use for such a state. Imagine we're dealing with a magnetometer. We're trying to measure magnetic fields. What would normally happen is at the center of that magnetometer we would have a spin or a magnetic moment which is precessing around the direction of whatever magnetic field we are measuring. And we are looking at the frequency of that precession because that's proportional to the magnetic field. And how do we measure frequency? We measure the phase of the spin at different time points, and we reconstruct that frequency. Now, it is important to measure tiny magnetic fields as precisely as we can. And so if we have just a transverse magnetization, it will evolve with its corresponding frequency, and we can turn that into a magnetometer. But if we have this multiple quantum coherence and we have multiple spins in the system, if we build such a state, it will evolve at the sum of all of the individual frequencies. And so we can measure a weaker field in the same time, or we can measure the same field faster. So a beta magnetometer can be built based on these multiple quantum coherences, and this is where they are used a lot these days. We will encounter these states as a part of our natural exploration of practical magnetic resonance pulse sequences in biology, but such states exist, and they are in practice instrumentally useful. So I will only just mention them here, and as soon as we meet them, we will meet them, and then this property will start making sense in the context of some practical applications. And finally, the second group of states, they're called correlations. And in exactly the same sense as there, if we have a product state between multiple spins, for example, involving a unit matrix on the first spin, chron Sx on the second spin, chron Sy on the third spin, chron unit, chron, and so on. So multi-spin system. The number of non-unit operators in such a state is called the order of correlation. That is, for example, a 2-spin correlation. If we have 3 such non-unit matrices, it will be a 3-spin correlation, and so on. In a lot of cases, we have a multi-spin system, and as a result of natural evolution under J-couplings, for example, we will populate, in fact, 3-spin, 4-spin, 5-spin, and higher order correlations. They are occasionally even useful. We do have triple quantum filtered experiments, for example, that do involve 3-spin correlations as intermediate stages, but I don't think you will meet highly correlated states in this module, because NMR at high temperature is almost by definition a weakly correlated technique. Okay, now the final item on the agenda today is a matter of computational convenience, and also a little bit of a prep for situations when we deal with dissipative dynamics. So sooner or later, we will have to introduce that T1 and T2 back into quantum mechanics, because we had them at the level of the Bloch equations, but remember, we abandoned it when we went to solve Schrödinger's equation, because there is no dissipation in Schrödinger's equation. But now we have the ensemble, the dissipation makes a comeback, and we need to introduce a little bit of mass to prepare for that. So that is item 4, Liouville space. Again, little to do with Joseph Liouville and a lot with John von Neumann. Let us take a look at our equation of motion for the density matrix again. We had d rho by dt was minus I h commutator rho. And the solution was that rho of t is E minus I h t rho of 0 E plus I h t for time-independent Hamiltonians. Turns out computers really hate double-sided matrix multiplications of this kind. So here, that's minus I h rho minus rho h. Let us remind ourselves how matrix multiplication happens in a computer. We have this matrix and that matrix, and this one we are interested in columns, and that one we are interested in rows. And so we multiply, taken in a product of every column with every row, and this is our matrix product. Remember how computer memory is organized. The values in memory are indexed linearly. There is just one number for the memory cell, and there's the values that the cell contains. Linear memory access in computers is really fast. We tell the memory controller, look, we want the values from here to here, and it just starts streaming them. Random memory access on modern computer architectures is very slow. Remember what I told you about the speed of light a few days ago? There are 20 centimeters to fly between the CPU and the memory banks in a typical PC. That's about a nanosecond at the speed of light in copper wire. So it takes nanosecond for the data to start arriving. If the data arrives in a predictable way, it just starts streaming it. So the data keeps arriving because it knows the interval of memory cells which to deliver. However, if the memory access is random, we need to keep telling the memory controller, and now we need that data piece, and now we need this data piece. And so the latency before the data starts arriving will increase sharply. We will have to spend that nanosecond every time we request a data point. So any matrix that is stored sequentially, for example, by rows here and by columns there, can be retrieved and multiplied rapidly. If we start addressing this matrix by columns or that matrix by rows, that will be significantly slower, particularly in situations when these matrices are stored as compressed sparse arrays. So you only store non-zeros and you do not keep the zero elements because, well, there's no point. But look at what we have here. If we store this Hamiltonian by rows and this density matrix by columns, brilliant. They'll get multiplied quickly. But then this multiplication will be a mess because they're stored the wrong way around. And so logistically, in a lot of cases, it helps to find a formalism where the equation of motion still kind of looks like the original Schrödinger's equation, which, remember how it looked. It was d psi by dt was minus I h psi, and its solution had been psi of t is e minus I h t psi of 0. Notice here, firstly, in spin dynamics, psi is a vector, and secondly, should actually be a hat in here. Secondly, the multiplication is one-sided, so if we store this Hamiltonian sliced up by rows, then we do not need to incur that penalty. And a lot of other things get simpler as well. So, what was done in there by, if memory serves, who invented Liouville space? Probably von Neumann himself as well. What we can do is we can say, okay, d rho by dt is minus I h superoperator rho, where we define this commutation superoperator as, well, whatever it means, right? The commutator, like that. Then the solutions for that are going to look like solutions of Schrödinger's equation. So rho of t will be e minus I h superoperator t acting on rho. There is a problem with this in that when we do that transformation, rho becomes a vector, so we stretch this matrix into a vector, which just puts the columns one under the other. Of course, the matrix dimension increases significantly. It becomes the square of the original dimension, so we use a lot more memory to store that. But the practical advantage of this is a lot of other operators in magnetic resonance, namely relaxation, chemical kinetics, spatial transport like diffusion and hydrodynamics, and so on. They are actually superoperators of this type. We will look more into that when we deal with relaxation theory. And so this formalism is a lot more flexible and extensible than the original Liouville von Neumann equation here. So there are two reasons why this is introduced. One is certain amount of computational logistics. The calculations do get a bit slower because dimensions do rise, but a lot of headaches are removed from programming and memory management. And secondly, when we start dealing with really sophisticated magnetic resonance things, like localized magnetic resonance spectroscopy, so when you want a specific voxel of your brain and the spectrum of that voxel, then you do have to worry about a great number of other things apart from spin dynamics. This kind of formulation is a lot friendlier to introducing all of the external kinetic transport and dissipation effects than the original equation had been, and that's the subject of the next few lectures for us. Okay, the summary. is, turns out, Boltzmann law has been very carefully designed, I suppose, by Mr. Boltzmann, and it can be ported to quantum mechanics without much difficulty. We simply notice that the probabilities that Boltzmann had derived, namely that, and you should have had your statistical thermodynamics courses by now, we can simply put them on the diagonal of the density matrix, rely on the fact that a thermally equilibrated ensemble is uncorrelated, and so there will be no off-diagonal elements here. We remind ourselves how to create a matrix with just one somewhere and zeros everywhere else. It's an outer product of two vectors. If we create such a beast, these are outer products of our basis wave functions, that's the probability, that's the partition function, then we arrive at the fact that the thermal equilibrium density matrix is proportional to the exponential of our Hamiltonian. At high temperature, we can expand the exponential in the Taylor series. We then realize that that's just a unit matrix minus the Hamiltonian, and then we additionally realize that this unit matrix neither evolves nor in fact influences any observables, so even that in most cases can be dropped, and so the thermal equilibrium density matrix is just minus a multiple of the Hamiltonian. Roughly speaking, the higher the energy, because of this minus, the lower the relative probability of the state being populated. So the high temperature approximation. Then we looked at the classification of multi-spin systems and the quantum states inside them. A reminder that the wave function of the composite system, or a state vector in our case here, because of how probabilities combine, they combine multiplicative in a multiplicative and combinatorial way. So the combinatorial product of the two state vectors, namely Kronecker product, is what we want. And this is how it looks. We just take an entire vector A and an entire vector B and replicate the second vector with the coefficients of the first vector, so we do get 4 states. This is how it is applied to specific numbers. If we have some linear combination, a little bit of alpha and a little bit of beta in system 1, a little bit of alpha, a little bit of beta in system 2, then the 4 coefficients pertaining to possible combinations in system 1 plus 2 are just products of those individual numbers, and the normalization is preserved. If we apply that to the definition of the density matrix, so Kron here, Kron there, and use the property of Krons, turns out predictably from statistics, if that is a table of every possible probability in system A, that's likewise for system B, then the Kron is a bigger table of every possible combined probability in which individual probabilities had been multiplied together. So as per the definition of the density matrix, we still have a probability table. For the Hamiltonians, we want the Hamiltonian of A to still act on A and do nothing on B, the Hamiltonian of B to still act on B and do nothing of A, and we want the energies to add up. So this is how the Hamiltonians are built of independent systems, and when we want them to start interacting, we need to take Kronecker products of some operator here and some operator there, and that would make the corresponding observables interact. And if we look at the operators that turn up either here or turn up in the density matrix once it's evolved for a while, that's the classification. You can have longitudinal magnetization states which interact with the magnetic field and correspond to a bulk magnetization of our now ensemble. If you look at these correlated states after a little bit of analysis of probabilities, turns out that they do not constrain the absolute direction of any spin, but they constrain their relative direction. So they're at liberty to move however they like, but they must move in a correlated way, which is why the thing is called correlation. Likewise, for magnetization, you can have transverse magnetization, you can have transverse correlation, and you can have weird correlations between different spins in the system, different directions as a result of different interactions. We will meet them in due course. That's, for example, the X projection of spin 1 being correlated in that same way with the Z projection of spin 2. And these states are also there. There is an obscure entity called a coherence, which is going to make an appearance in due course. I've just given you the definition here and made a brief note that it is useful in a lot of cases in magnetometry and also in protein NMR experiments where we use it to filter magnetization from some unwanted states. A general thing where you've got a multi-spin system and you've got anything here, cron Sx on spin 2, cron Sy on spin 3, cron no particular prescription for spin 4. So this is a 4-spin system with the second and the third spin correlated and maybe something else in there. This is called a multi-spin correlation, and if you've got 3 or more non-unit operators, then it's a 3-spin correlation, 4-spin correlation, and so on. And finally, a little bit of preparation for the next lecture. Turns out computers are a lot happier when we only ever multiply a matrix by a vector, always from the same side. If we don't, a lot of things get a bit messy, and that's best avoided. And it turns out that Liouville von Neumann's equation is an instance of that mess. And so what merits our attention is a way of working around that. We remember that Schrödinger's equation didn't have that problem. Right? Psi is a vector, matrix exponential is a matrix, and so this is matrix times vector always from the same side. This would be a lot friendlier on the memory controller. And this, the so-called adjoint map in the theory of Lie groups, but for us they are called commutation superoperators. We just did a cosmetic renaming really. At this point it's all it is. We introduced H double hat, which acts on rho from just one side, and it is defined as this commutator. And we will go into the particulars in a few lectures from now. And then of course that looks mathematically just like the original Schrödinger's equation did, just in a space of a much higher dimension, and the solutions are there for one-sided multiplication by that superoperator onto the density matrix, which in this case comes stretched into a vector, just one column underneath the other. So that is called Liouville space, and that we will use when we start dealing with relaxation, kinetics, and hydrodynamic transport in these systems. All right, any questions?